Oxidation numbers.
Where are the electrons in the molecule?
Where the electrons are at in the molecule.
This is like Where's Waldo then, right? We're going to try to find electrons.
Yeah, with math.
Cool.
Where's Waldo with math?
Awesome.
So the electrons, like we've kind of talked about, they're not distributed evenly when you draw the Lewis structures, and you have polarities and things. But this is going to help us visualize kind of where they're at by assigning more or less a charge to a covalent compound to see if the electrons are evenly distributed throughout the molecule.
Okay, so we have some rules. We actually have 7 of them. We're just going to go through them real quick. You have to know and memorize these rules.
Because you're going to apply them for this podcast and the next one. The next 2 podcasts, they talk about another type of reaction. We just learned 4. These are going to be about redox reactions. You've probably heard of oxidation before.
Like the Statue of Liberty.
The Statue of Liberty, like it's oxidized,
right.
It turned to green. Rust, it's like, oh, something that just got oxidized. Well, there's a reason for that. It's because of this type of reaction. First thing we're going to start with is ions. You're familiar with ions. They have positive and negative charges. If you have an ionic substance, assign the normal charges to that ionic substance.
So if you have a substance like sodium chloride, which is
NaCl. Sodium is +1.
Chlorine is -1.
Chlorine is -1.
That's their oxidation numbers.
That's their oxidation number. And just like with ions, if you have an element, it is not an ion. It does not have a charge. It's 0.
So if we have the pure element francium, for example, it does not have an oxidation number.
0. If we had sodium in its normal state, not sodium chloride, that's an ion, but regular sodium by itself,
Elemental
it's an element,
sodium.
Elemental sodium, 0, no charge.
All right.
Or oxidation state. Hydrogen.
So in covalent compounds, the hydrogen
is +1.
Is always +1.
Now, it's +1 in ionic, so what's the difference? Well, yes, it is. But we're really, these next 2, we've got oxygen as well, hydrogen and oxygen, +1, -1. Those are their normal charges for ionic substances.
Oxygen's -2.
Oh, -2. Yeah, you just believe your eyes, not your ears. Oxygen is -2. Those are the normal charges for ionic substances, but now we're trying to assign quote-unquote charges, oxidation numbers, to covalent compounds as well. So here's where it gets tricky. These are going to be our starting points here. Hydrogen, oxygen, ions, and elements. But if it doesn't fit that list, then you have to start doing some math and cancel out charges to get a neutral molecule, because molecules have to add up to 0.
So a neutral molecule like carbon dioxide, for example.
There's no charge on that.
Right. So its oxidation numbers for the carbon and the oxygen have to all add up to 0.
Just like sodium chloride, +1, -1, they add up to 0. This is why we crisscross ions, because we want them to cancel out. Same thing with oxidation states, we want them to cancel out. Remember, oxidation states are kind of like charges, but with covalent compounds as well. Polyatomic ions. Now, if you had something like hydroxide,
OH -1.
OH, there's a -1 charge on it. So we don't want those to cancel out. We want them to add up to the charge, -1 for hydroxide.
And you know what? That works out really well because oxygen's always assigned an oxidation number of -2.
And hydrogen's 1. So if hydroxide is a combination of O and H, -2 and +1 gives you that -1 charge if you're looking at those 2 elements in 3 and 4.
Actually makes some sense.
Yeah, this is a good example because hydroxide, O and H are right there on the screen for him to look at.
Yeah, good thinking, Mr. Manner.
Yeah, I try. I really didn't plan that. It just kind of came out of me. Sometimes brilliance just comes out of me.
Hey, rule 7, because good things always come in 7s.
It's a lucky number.
All right. Halogens are pretty much always going to be -1 because they're pretty strongly electronegative.
So they like to pull those electrons in the covalent molecules. So we say they have an oxidation state of -1. They don't have to be -1. If it's an element, it's 0. But if you don't have any of these other rules present, start with the halogen, it's -1, and then figure everything out from there. So let's apply these rules then. Keep this list of rules out as we go through these practice problems. Here's the first set. These are simple practice problems.
Wow. That was exciting.
I discovered the transitions. That was a little transition overload, I'm sorry.
That was pretty
Just
awesome.
making sure you're paying attention. It was pretty good.
I was especially blown away by the explosion one.
Yeah, it's like all the comets were coming towards the middle, and then there was an explosion.
Yeah.
And if you didn't catch it, rewind it in slow motion. It's
It's like
even
I was
better.
watching Transformers or some other Michael Bay movie.
Yep.
That's enough rambling.
So we're going to apply our rules. See which categories these fit into. Sodium, by itself, nothing else attached to it, 0. It's an element.
All right, elemental sodium, oxidation state of 0, easy.
Oxygen, O2, element.
Yeah, there's 2, right?
But it's still an element.
Oh, okay, elemental oxygen.
Element 0. There's
Good to
nothing
remember
else,
on that one.
Nothing else attached to it. It's still an element 0. Sulfur.
Ooh, that has a -2 charge.
Yeah, it's an ion.
Charge.
Ions keep their charges.
Yes.
Pretty good. Sodium, positive, keeps its charge. It's +1. It's the ion rule.
You weren't kidding when you called this simple practice.
Very simple practice.
All
Okay,
right,
let's step
I
it
like
up a little bit. Now we've got a molecule, H and F.
We want the oxidation states to add up to 0, right?
Yeah, and we want an oxidation state for each atom. Hydrogen, and there's a rule for that, +1. Halogen, there's a rule for that, -1. Look at that, they add up to 0. All right.
Nice.
And this is an ionic substance, so that makes sense.
Yeah.
MgO, oxygen, we have a rule for that.
-2.
That's -2. Magnesium is ionic. This substance is ionic, so what's the charge of magnesium?
We want the oxidation numbers to add up to 0, right? So it's got to be +2.
+2.
And that's its charge on the periodic table.
So it fits 2 rules. It has to add up to 0, and it's ionic, and magnesium is always +2 when it's ionic.
Cool.
Okay, now we've got to think a little bit down here.
So?
The next molecule, yeah. So, sulfur monoxide. Now, we don't have a rule for sulfur, and it's not ionic. We do have a rule for oxygen, though.
It's always -2.
Oxygen is always -2. So,
The molecule has to add up to 0.
it has to add up to 0. Since there is only 1 sulfur and 1 oxygen, this has to be +2 to equal 0.
It's +2 and -2.
Now, this
Add
is
them
where
together.
there's a big difference between oxidation states and charges. Sulfur on the periodic table, when it's ionic, is -2. Okay? This is not an ionic molecule, so this rule does not take effect. Sulfur is +2 because it's attached to oxygen. Oxygen is -2, therefore sulfur is +2.
All right, sodium. I think we did this one already.
We did, just in case you weren't paying attention.
Element.
It's by itself, it's 0.
And
Whoa,
then
noble gas, slow down. XeCl4.
noble gases bond.
One of them does, this one does.
Oh, cool.
Let's look at the oxidation state. Chlorine,
That's my favorite noble gas, by the way.
halogen, Xe. Okay,
Yeah, sure.
fun fact. Chlorine, there's a rule for that. It's a halogen, it's -1.
All right. We have 4 of them, though.
4 of them, so that total, just like we did ionic now, that total is -4.
Okay.
So if we want it to add up to 0, we've got that -4. The 1 xenon has to be +4 to cancel out those 4 negative ones.
Okay, so +4 plus 4 negative ones
4 negative ones.
adds up to 0. That makes
Negative
sense.
4. Okay, so just like we did with ionic, a little bit of practice with those rules. You find a rule that fits one of them and use it to figure out the other. All right, now we're going to get into some more complex practice. It's raining ions. Not quite as dramatic as the last transition, but still very effective. Okay, now we've got polyatomic ions. We've got charges to deal with. We've got more than 2 atoms, so let's kind of break them apart. NO3 minus, that -1, that's a 1 there, is very important.
All right, so that's one of those examples where we have a polyatomic ion, and the overall charge is -1. So we don't
-1.
want the overall oxidation states to add up to 0 in this case.
We
They
want
should
them to
add
add
up
up
to
to
-1.
Start with the oxygen. We still have those rules, -2. There's 3 of them. That gives me -6. All right. But I don't want this nitrogen to cancel it out to 0. I want it to be -1.
Okay.
So this nitrogen, this 1 nitrogen, has to be
Positive 5, because positive 5 and negative 6, negative 1.
Negative 1. So the nitrogen, here's what we say. Even though there's 3 oxygens, the nitrogen is 5, the oxygen is negative 2, and the 3 oxygens add up to negative 1.
So we're talking about the oxidation state of each atom in the
Individually.
compound.
Each oxygen is negative 2, nitrogen is positive 5, they add up to negative 1. All right, let's try this now with the carbonate. Negative 2. There are 3 of them, so that gives me negative 6.
And this is another case where we have a polyatomic ion, so we want it to add up to negative 2.
Negative 2.
Not 0.
So this has to be 4
All right.
to cancel that out. So the carbon is 4, the oxygen is still negative 2. IF2. Uh-oh. This is tricky.
Well, it doesn't have a charge, so that makes it easy. It all adds up to 0, right?
It all adds up to 0, but I've got 2 halogens.
They're both negative 1.
But that
No
wouldn't
big
add
deal.
up to 0.
Oh.
You're adding 2 negative charges. So what else do we know? Remember, we're talking about electrons. What other term do we know that affects electrons?
Well, I know fluorine's kind of a special element in it that is the most...
Electronegative. I see where you're going with this. Electronegative.
So it's probably going to be the negative one.
It's going to be the negative one because it's electronegative. It's pulling the electrons towards it. It's stronger than iodine. So we're kind of combining things from the last unit. That's the one that's going to be negative 1. That means the iodine does not have to be negative 1. I've got 2 fluorines, negative 2.
I want it to add up to 0.
So the iodine has to be positive 2.
All right.
And the fluorine is negative
And
1.
each fluorine is negative 1.
And there's 2 of them. All right.
Great.
OH minus. Hey, that's that example we did.
I think we talked about this.
But now you get to see it
Perfect.
written out. There's a rule for oxygen. There's a rule for hydrogen. Those add up to negative 1, and life makes sense.
Awesome.
All right.
Oh, this one looks like difficult. Looks like it's an ionic compound with a polyatomic ion in it.
It is. So we can handle this a couple of different ways.
This is crazy.
Here's what I like to do. You got pretty high on that little falsetto. The oxygen,
Been
well,
practicing.
we still have a rule for that, negative 2.
All right.
Awesome. But
Molecule adds up to 0, though.
it does
still,
add
right?
up to 0.
Yeah,
It does add up to 0.
that is important.
The hydrogen is positive 1. There's a rule for that, right? So now we're doing the same math, but with a couple of different things. There's 1 oxygen, it's negative 2.
Mm-hmm.
The hydrogen is positive 1.
And we have 8 of them.
4 of them. Oh, there's a 2 outside that 2
Yeah.
distributes. We have 8 of them. That's
8
positive
hydrogen.
8. Positive 8, the 2 distributes.
Yeah.
Okay, now this is a hard example for a couple of reasons, because all of this needs to add up to 0.
So we need to put the nitrogen in there. So we've
Okay,
got
so-
positive 8 and negative 2. What does that add up to?
Positive 6.
Positive 6.
So that means I need this to be negative 6 to cancel all of that out, right?
Yeah.
Okay, so oxygen's negative 2,
Pay attention, though.
hydrogen's positive 1, nitrogen's negative 6.
What? No, wait. What?
Oh, it's not negative 6. Why?
We do have 2 nitrogen still. The 2 distributes, like you said.
There's 2 of them. That means each one has to be negative 3. Very similar to what we did with ionic bonding. You have to pay attention to how many you have. Total, the nitrogens add up to negative 6. Each individual one, however, is negative 3.
This is a really good example because this is, to be honest, this is about as difficult as one of these problems could become.
It is. So if you did not understand that, ask for help. Last one, and then we're done. Polyatomic ion, magnesium. Let's see what we have. Oxygen, minus 2.
Jinx.
Hydrogen, plus, I guess I have to stop talking then. You jinxed me.
Oh. How does the jinx end? I don't even know how this works. Oh. All right, so oxygen's negative 2, hydrogen's positive 1. We actually each have 2 of those, though. So we've got positive 2 from the hydrogen and negative 4 from the oxygen. And we want the molecule to add up to 0.
Because there's 2 of each. Dang it.
Oh!
All right, game over.
You lose.
Negative 4 and positive 2, because there are 2 of each of those. We want them to add up to 0. So that means, looks like the magnesium is positive 2.
Hey, that's its charge in an ionic compound.
Oh,
too.
it is. I could have done that, couldn't I?
Yeah, awesome.
You can
right.
also think about that. Each hydroxide is -1 because of the 2 and the 1.
Oh.
So you've got 2 -1s. The magnesium is +2. It's ionic. So even though there's 3 of them there, the magnesium is still a single ion. You can just treat it as its normal charge.
Yeah, you can see there's actually more than one way to solve these problems.
Yeah.
Which is pretty typical of chemistry.
Just like there's more than one way to skin a cat.
Ew.